Welcome to Oxidation Reduction, or Redox, Lecture A. Today I'd like to talk to you about rules for assigning oxidation numbers, recognizing oxidation and reduction, recognizing oxidizing and reducing agents, and balancing and writing balanced half reactions. So let's get started. If you take a look at the rules that we have for assigning oxidation states is just simply a fancy way to say charge. That's usually what I'll say is charge. And all that means, of course, it could be +1, -1, +2, -2, or it actually could be 0. Just like in the case of an element. If I have a standalone element, whether it is diatomic or not, a standalone element's oxidation state is going to be 0. Like if I have a chunk of iron just sitting there, its oxidation state is 0. But if I have an iron +3 ion in solution, then its oxidation number is the same as its charge, which would be that +3 that we talked about. So say, for example, I have a sodium ion or a chloride ion. You can see the sodium ion is +1, chloride ion is -1. Fluorine being the king of electronegativity, it always gets to be the negative guy, so it is always going to carry a -1 charge regardless of whether it's paired with a metal or another nonmetal. And oxygen, being right next to fluorine, is also pretty highly electronegative, so it is usually going to be -2. Now there is one exception. In our polyatomic ions reference table E, you will find the polyatomic ion peroxide. And peroxide's formula is O2 - 2. So it would stand to reason if I have 2 oxygens and they add up to -2, each one must be -1. So that is a pretty unusual exception. Another unusual exception is in the rare case that oxygen might get together with fluorine. Fluorine's electronegativity is higher no matter what. So oxygen's going to have to carry the positive charge. If I were to combine them together in a compound, it might look like this, OF2. And in that case, fluorine would get to be the negative guy, and the oxygen would have to carry a +2, but clearly that's pretty rare, just specifically for that instance. Then another one that we can usually count on is hydrogen. Hydrogen being +1 in covalent compounds. But there is a situation that hydrogen can be in an ionic compound. If hydrogen is going to pair up with something less electronegative than itself, like for example, lithium, sodium, potassium, rubidium, cesium, or francium, look at where all those guys are. They're below hydrogen in the periodic table, so therefore they have a lower electronegativity. If they have a lower electronegativity than hydrogen, then hydrogen has to be the negative guy. So say, for example, I could have LiH. That's a metal and a nonmetal. That is ionic. And in that case, lithium would have to carry the positive charge because of the lower electronegativity, and hydrogen would carry the negative charge. And when that occurs, again, that's ionic because it's a metal and a nonmetal, and that's referred to as a hydride. But again, that's pretty rare. It's limited to those items that are below hydrogen in the periodic table. So let's practice. As we look at assigning oxidation numbers to each element, what we can see here, we said hydrogen, as long as it's not combined with something below it in its column in the periodic table, it's going to be +1. Oxygen, it's not a peroxide, so it's going to be -2. And let's see what occurs there. I've got 2 hydrogens at +1 each, so that would stand to reason. That's kind of like a running total of -2. I have 1 oxygen at -2 each, so that's like a running total of -2. And so, of course, what can we see here? If I have a neutral compound, then the sum of the oxidation numbers must be 0. So let's take a moment and jot that down. Sum of oxidation numbers in a neutral compound, meaning electrically neutral. In a neutral compound must be 0. So now let's look at that P4. P4, it's a standalone element. We just said everything has to add up to 0. If you're standing there all by yourself and you've got to add up to 0, guess what? You're 0. So here in this standalone guy here, phosphorus is 0. We look at Na and Cl. Na being in group 1 is +1. So therefore our chlorine is -1 in that ionic compound. Now let's talk about going with 3 different elements to assign their oxidation states. I have hydrogen, we said we could count on it as +1, and oxygen we said we can count on as -2. So you can see we save that sort of wild card as our last of the 3 because we can rely on the fact that everything has to add up to 0. So I have 2 positive 1s. So if I'm doing a running total again, then hydrogen is +2. If I look at my oxygen, I have 4 -2s. That's -8. And now I need +2 and -8 have to add up to 0. So -8 being bigger, I must have to have sulfur at +6 to get everything to add up to 0. I only have the 1 sulfur. It doesn't have to split that +6 charge among many members, and so that 1 sulfur must carry the +6 charge. Then, our very last guy on the page here, we have copper and we have nitrate. And what you may wish to do is, at least to figure out the copper, is realize this is an ionic compound. It's a metal and a polyatomic ion. So I see I have 2 sets of nitrate. Nitrate as a set is -1, so my negative side is -2, so therefore my copper here must be +2. And we know that oxygen we can usually count on as a -2, so we're going to do our wild card last. And so our wild card is going to be that nitrogen. And let's take a look at trying to make sure everything adds up to 0. So I have 1 copper is +2, and I have 6 oxygens at -2 each is -12. And we know everything has to add up to 0. So as I look at -12 being bigger, we know that the nitrogen has to work out to be a total of +10. But you might notice that that +10 has to be divided amongst 2 nitrogens. So therefore the charge on each is +5. So notice I did 2 things. I did top, and then sometimes I went to the bottom in blue. And the top in black is what we want. We want the oxidation number on the individuals, not the oxidation number of totals or of multiples. So this was oxidation number of individuals, and that's what we want. I only did this down here to figure out that I had to add up to 0. So this is the oxidation number of multiples. That's not what we want. We only want it on the individual. Again, I did that stuff in blue just in order to help us see or to justify where the answers came from. So now let's talk some vocabulary. You heard us talk about oxidation number. Well, now let's talk about just purely oxidation. If I have, say for example, a metal like iron, what we know is that metals can generally be in 2 oxidation states. They can either be 0 or positive. That's pretty much it. So let's talk about changing iron from 0 to positive. Well, let's just pick one. We'll pick +2. What you might notice is, how did it get to be that way? If I'm going from 0 to +2, I had to lose 2 electrons because my charge is positive. Remember, losing an electron, remember electrons are negative, right? Losing an electron, that's a double negative, so that's where that positive came from. So when you lose electrons, what you will notice is that the charge goes up, or the oxidation state goes up. Charge goes up is oxidized. Easier to see maybe is charge goes down is reduced, right? When someone decreases the amount that they charge me for something, sometimes they say the price is reduced. So the charge goes down when you are reducing or when it's reduction. But what you'll notice here, the first one I just did here was oxidation. And so my equation right now is balanced according to mass. But it is not balanced according to charge, because one side, my charge is 0, the other side, it's +2. So I have to balance my half reactions that I just wrote for oxidation by adding electrons to the high side, again, electrons being negative, to bring them down, that high side down to match the low side. So I've got 0 and I've got +2. +2 is my high side. I'm going to add 2 electrons to the right-hand side, and so now they match. Both sides of the equation are neutral. They don't have to be neutral, they just have to match. So let's talk about some things that happened here. When our iron atom was oxidized, it lost electrons. There's evidence of that in my half reaction, because when I balanced it, my electrons were given off as a product. They were on the right side of the equation. You'll also notice we said the charge goes up, or a fancy way to say that is the oxidation state increases. So now let's talk about the opposite scenario. Let's have something become reduced. Let's look at chlorine, elemental chlorine. And hopefully we can recognize that its oxidation state is 0. And as an anion, chlorine's charge is a -1. And so what did I just see? My charge went down. And so this is a good example of reduction. When I first showed you the half reaction for iron, I said that it had to be balanced according to mass and according to charge. My half reaction for iron was already balanced according to mass because I had 1 iron on both sides. But what you will notice with chlorine is that I have 2 chlorines on the left and I have 1 on the right. So I need to balance this half reaction with a coefficient in front of that chloride ion. So I'm now balanced according to mass. Next, I have to consider balancing according to charge. And what I will see is that on the left side, my total charge is 0, or it's neutral. And on the right side, my charge is now -2. So I have to add electrons to the high side, which in this case is the 0 side. And I need to bring it down to match the low side. So you will notice now that I'm balanced according to mass and I'm balanced according to charge. Now you'll see that both sides are -2. As we said, they don't have to be neutral, they just have to match. So when it comes to reduction, the charge is going to go down if you take on extra negative charge. So reduction causes a gain of electrons. And what you will see is that our oxidation number or oxidation state or charge decreases. We went from 0 down to -1. You'll also see that gain of electrons due to the fact that when I wrote my half reaction, I had to include those electrons on the left. They're being taken in as a reactant. That means they are being gained. Quick and dirty, talking about loss of electrons is oxidation, gain of electrons is reduction. You may find the following items helpful. We can say that oxidation is loss of electrons, and reduction is gain of electrons. Another thing we can say is Leo, as in lion, goes grrr. And how could that possibly be helpful? Loss of electrons is oxidation. Gain of electrons is reduction. And now for the very last item, agents. You'll see that oxidation and reduction is kind of a circle. Oxidation is losing electrons, reduction is gaining electrons, and they're all intertwined together in one way, shape, or form. So very often, by losing electrons, I enable gaining them to occur by somebody else. So as we said, they're related. If I'm going to lose my electrons, I enable, in other words, if I'm going to be oxidized, I enable reduction, which is gain of electrons, to occur. So by enabling, you're often referred to as an agent. In other words, if I am oxidized, I can be referred to as a reducing agent. And if I am reduced, I can be referred to as an oxidizing agent because I allow or I enable that other thing to occur. So here, if we had to label who's oxidized, we would say it is iron 0. If we had to say who's reduced, we would say it is the Cl plus the Cl2 is reduced, 0. If we had to say who is the reducing agent, we would say it is the iron 0. And if we had to say who is the oxidizing agent, it is the Cl2, 0. In other words, they always want who's oxidized, who's reduced, who's the oxidizing agent, who's the reducing agent. You always shoot for the guy on the left-hand side of the arrow, the before, not the after. So now let's practice. Let's identify oxidation, reduction, and all of our agents. In order to do that, it would be a good idea to record oxidation numbers for everybody. So our standalones here are 0 and 0. Aluminum is +3, and iodine is -1. Hopefully we can all see that. So what do I see? My aluminum 0 goes from 0 to +3. So aluminum 0 is a player here for sure. Its oxidation number went up. So we know that aluminum 0 is being oxidized. We also know agents are opposites. So aluminum 0 is also a reducing agent. When I look at the iodine goes from 0 to -1. So I can see that its charge went down. My iodine, try that again. With an oxidation number of 0 is being reduced. Again, we always want the guy on the left-hand side of the arrow, and as a result, it enables oxidation to occur, and so it is referred to as an oxidizing agent. So that one was a little simple. Now let's look at one that's a little more complex. We've got lead is +2 because sulfur is -2. Oxygen standalone, 0. Lead +2, oxygen -2. Oxygen here -2, but I have 2 of them, so that's -4. So each sulfur there is +4. So let's see who underwent a change in oxidation number. Did lead undergo a change in oxidation number? And the answer is no, it didn't. Did sulfur undergo a change in oxidation number? Yes, it did. I can see that my sulfur went from -2 to +4. So sulfur's charge went up. Sulfur -2 then is our guy who is oxidized, and it is the reducing agent. Now let's look at the last element is oxygen, and we can see that oxygen went from 0 to -2. It went from -2 and it went from -2 here as well. So we know that on the right-hand side, they're both -2. So O20 is our other player in oxidation and reduction. Its charge went down, so it is being reduced, and therefore it is the oxidizing agent. So now let's take it one step further. Now that we can recognize oxidation and reduction, let's practice writing half reactions. I know that these standalone guys are both 0. This is +1. This is -2. So what do I see occurs? My lithium is oxidized and my oxygen is reduced. So I'm going to write some half reactions here. I've got lithium 0 going to lithium +1. Notice I did not carry that subscripted 2 with me. I can balance this according to charge by putting 1 electron on the left-hand side. My oxygen, my O2, I do carry that subscript with me because it is a diatomic molecule. And it's going to oxygen -2. Balancing according to mass, I would put a 2 in front, and balancing according to charge would require a gain of 4 electrons. Looking ahead. If I look ahead, what you will notice is, I put my electrons on the wrong side here, hello. What you will notice is, as soon as I fix this, we will notice it, that my 1 electron goes here. What you will notice is that I have a loss of 1 electron and a gain of 4 electrons. If I lose $1, is someone else going to pick up $4? I don't think so. So eventually you can see we're going to lead into needing to make the loss equal the gain, but that's for another day. Let's take a look at our next example. Standalone zinc, 0. Sodium +1. Oxygen -2. And, we might need to do a running total. I have 2 +1s is +2. I have 4 -2s is -8. So here my sulfur must be +6. So I've got my sulfur there at +6. If you've got a really good memory, you might remember we already did something with sulfur being +6. And notice that it was part of SO4, which is sulfate. Look at that, and look at this, sulfate. Once you do a polyatomic ion, it's always going to be that way. So if you're really good at just kind of remembering things, you'll see very easily that, again, zinc at +2, -2, there's another SO4. This guy must be +6 again. And our sodium here is 0. So whose charge changed? I can see that zinc went from 0 to +2. That's oxidized. Its charge went up. I can see that sodium went from +1 down to 0. Its charge went down. So that's reduction. So zinc was the guy who was oxidized, and our sodium was the guy who's reduced. So let's write some half reactions. I've got my zinc 0 going to zinc +2. Take the high side down, bam. I have sodium, not a diatomic element, so I'm not going to carry that 2 with me. +1 going to sodium 0. Bring the high side down to match the low side, and there we go, balanced half reaction. The next one's really easy to see. They pretty much gave us all the oxidation numbers. Iron's going from +3 to 0. That's reduction. Bring the high side down with 3 electrons to the left. Calcium 0 is going to calcium +2. Bring the high side down to match the low side. Notice they don't usually give you the zeros, but I write them in. It's just for me to say to myself, hey, Coos, don't forget, girl, that's a 0 right there. And it just reaffirms it for me. So our last one is very similar. We have sodium 0 going to sodium plus 1, bring the high side down to match the low side, and hydrogen goes to H2. I do have to carry that 2 with me because it's diatomic, balance according to mass, and bring the high side down to match the low side. And there we go. That's all I have for oxidation reduction, Lecture A. I hope you enjoyed it. Have a good day.